Thank you, David, and I'm really grateful for the invitation to give these lectures. And I should say that the starting point for several of the results I'll be talking about were actually conversations taking place here 2 years ago during a summer school. So if you're starting a collaboration this week, you know what might happen in 2 years. All right, so the topic is going to be essentially Anosov representations, right? And there are going to be some locally homogeneous flows, which means that essentially it's going to be Anosov representations studied from the angle of hyperbolic dynamics. And we've already seen Anosov representations in Beatrice Posetti's lectures. I'll be giving definitions again, though. And but I'll start with a few basic things from hyperbolic dynamics, right? So the basic definition will be a hyperbolic set. So the setting is a flow which for now will be a smooth flow on a manifold M. And I should say that whenever I consider a flow, I always assume that it is complete, so it is defined for any real number t. And I will always assume that the flows are without global fixed points. So meaning that the vector field generating the flow never vanishes. Okay. So a hyperbolic set is a subset K in M. That can usually be drawn essentially as what it does to vectors, to tangent vectors. So if you're flowing out, starting at some point x for some time t, there's already one direction that you know, whose behavior you know under the flow, which is if you look at the vector field generating the flow, after time t, it will be transported by the differential of the flow to the vector field itself. Right? And hyperbolicity is assuming that you have, in other directions, you'll have some vectors that, when applying the flow to, will become very short after a long time. So this is what we'll call the stable direction. And you'll have some other direction called the unstable direction. No, these are vectors. These are just, yeah. WS will be in the lecture number 2 or 3, I think. No, not yet. So there will be another tangent direction called EU. Where here, on the opposite, if you start with a vector in this direction, it will tend to become very long. Okay. So it's typically what we want to call chaotic dynamics, which is like in different directions, you'll have very different behaviors of the flow, but on an infinitesimal level, right, on the level of tangent vectors. Right, so the exact definition would be that you're actually asking 3 things on the subset K. The first one is that K should be compact. Right, the manifold M is not assumed to be compact here, but K will have to be. The second one is that it should be invariant under the flow. So if you flow out from K, you stay in K. And the third condition, which is the one that we always see as the main definition, is this splitting of tangent vectors. So it means that you have a splitting of the tangent spaces to the manifold M, but only over points in K. Right? So the restriction of the tangent bundle to K splits as a direct sum, ES, E0, EU. And these are, well, you can always put in the definition that there are continuous vector subbundles that are invariant under the differential of the flow. And E0 will just be the direction of the flow, which is why we're asking to not have fixed points, so it's always one-dimensional. So E0 at a point x will just be the direction of the flow, and then ES will be contracted and EU will be dilated, meaning that that there are some constants, let's call them C and A, such that for any point in K, any vector in ES over the point x in any non-negative time, if you look at what happens to the vector V after some time t, it will get very short. It's an exponential contraction. And if you look at what happens to vectors in EU, it's the other way around. You apply the differential of the flow, and they become very long. Okay, so this is a very basic definition that probably a lot of you have already seen, maybe not everyone. A few things that should be said is that there has been a choice here to consider norms of vectors. Right? And so to make such a choice, you have to pick a Riemannian metric on your manifold. But this definition will not depend on that choice because we ask for K to be compact. And that's one of the reasons why we're asking for K to be compact. So if you look at the norm of V here, this is a norm at X. And so since X stays in a compact set, you can change the norm up to absorbing it in a change of the constant C. Right? So that's where the fact that it's compact is important. And if you look at the norms on the left of what happens to vectors after time t, this will be a norm over the point phi t of x. And phi t of x is also in your compact set K because K is assumed to be invariant. So same thing, it will not depend on the norm. And so this is really a definition depending just on the flow and its dynamics and not on the geometric structures outside of this. Okay, let's say goodbye to this one. Should be good. All right, so usually the first definition that you'll have, or the first example of hyperbolic set, is when the whole manifold is a hyperbolic set. So this is what we call an Anosov flow, and we'll hear more about those in Simeon Phillips' course. So that's still in this definition. So phi t is Anosov if M is a hyperbolic set. And here we're going to have to deal with some more general flows than Anosov, essentially, because Anosov means that you have this contraction, dilation of vectors everywhere in the manifold. But we're going to allow for some flows that may have some dynamics only happening on some subset of the manifold, and not everywhere. And we'll want this contraction, dilation thing to happen where the dynamics is actually happening. And so the definition here is what we call an axiom A flow. So phi t will be called an axiom A flow if the non-wandering set is a hyperbolic set and there's a second condition, which is essentially saying that the dynamics are only somehow happening because of periodic orbits, which is that this non-wandering set should also be the closure of periodic points. Okay, so I'll give the definition also of what we call the non-wandering set. Right, so you may know that dynamics is all about recurrence, right? It's about when orbits leave a point and come nearby the point, or you want to know where they go eventually. And so a non-wandering point, it just means that if you look at any neighborhood of your point, you can find orbits that will leave this neighborhood, or that will start in this neighborhood, flow out for a long time, and then come back to this neighborhood. All right, so the non-wandering set of phi t. This is the set of points in M. Let's say with sequences, you can find a sequence xk convergent to x, some large numbers tk, such that phi tk of xk also converges to x. Right, so periodic point just means that the orbit actually comes back to the very same point. So obviously, periodic points are non-wandering because you just take constant sequences here. But the addition in general is that the non-wandering set is always closed, which periodic points don't need to be. So any flow already satisfies that the closure of periodic points will be included in the non-wandering set. Okay, so from this definition, I should give a few examples. And the main, so let's say, factory to produce examples of hyperbolic dynamics is geodesic flows in hyperbolic geometry. Right? So we're going to start with a hyperbolic manifold, so essentially a discrete subgroup gamma of the isometries of HD. I'm thinking of real hyperbolic space here, but if you prefer the complex one, you may think of that. So this will be a discrete subgroup. Just in case I have questions I don't know how to answer, I will say that it is torsion-free. Although this will make some people upset. And just to have manifolds instead of orbifolds. Right, so from this subgroup gamma, you'll construct the hyperbolic manifold HD mod gamma. And to have a dynamical system here, what you're going to be working with is the unit tangent bundle of this. Right, so we'll call this M gamma, that you could also see as the quotient of the unit tangent bundle of the whole hyperbolic space HD. And this will have a flow called phi t gamma on the quotient, which is the geodesic flow. Right. And when you study the geodesic flow on a hyperbolic manifold, what you're going to start by doing is studying this flow on HD itself. Right? And you'll look at what the differential looks like, pick your favorite model of the hyperbolic space, compute this, maybe change your favorite model of the hyperbolic space after trying to compute it and failing to. And you'll realize that it already automatically has this structure of contraction and dilation on the hyperbolic space itself, although you're working with a very non-compact thing. Right? But because it will automatically have this contraction dilation on the hyperbolic space HD, the condition to get an axiom A flow on the quotient will really be in the compactness of this non-wandering set, and not so much in the, once you have a compact non-wandering set for this geodesic flow, it will automatically be hyperbolic. So that's a fact, which is that the geodesic flow on this quotient M gamma is axiom A. if and only if gamma is convex cocompact. All right, so convex cocompact is something we've already heard, I think. I don't know if we've heard a definition, so it's pretty simple. You have something convex, which is cocompact. So there is a convex set C inside of your hyperbolic space, HD. So convex, such that gamma acts cocompactly on C. Right, so if you were to draw this convex subset, you'll have to remove some parts of the hyperbolic space. Usually we'll draw this in dimension 2 by removing some areas bounded by geodesics. In higher dimension, you won't necessarily find things bounded by geodesics or totally geodesic subspaces, but you might have to add a few more. And by a few, I mean infinitely many. Right, so this will be your convex set C, on which gamma is acting cocompactly if you have a convex cocompact subgroup. And what will be the non-wandering set of this geodesic flow on the quotient? Well, essentially, to have a non-wandering set, the flow will have to stay in a compact subset, right? To have a non-wandering orbit, sorry. And what you can show is that the non-wandering set of phi t will be exactly, after quotient by gamma, will be exactly the elements of the unit tangent bundle, so pairs of a point x and a unit vector v, such that the flows always stays in that compact subset C. The convex subset C on which gamma is cocompact, sorry. So for any t, so now it's the geodesic flow of the hyperbolic space HD. This will have to stay in C. Okay. But your subset C actually is not unique here. There is a best one, which would be a convex hollow something, like the smallest one working. So if you want to have an intrinsic characterization of this not involving the choice of a convex C, what you can look at is try to understand this condition of staying in C, right? And this condition essentially is saying that on this picture here is that your geodesics cannot cross these things that you're removing, right? So for your geodesic to stay for all time inside the convex set C, this will just be a condition on the endpoints at infinity of the geodesic, right? So this geodesic will have two endpoints, one which is V plus, and the other one that we'll call V minus. And the condition is that both of these endpoints here will belong to the limit set of gamma, sorry. So that's another definition I should state, sorry. I guess this was in Barbara Shapiro's lectures already. So the limit set, lambda of gamma, this is the accumulation points of orbits in the boundary. Right? So this is, what you do is you pick a point O in the hyperbolic space, look at the orbit of this point, and consider accumulation points on the boundary. Well, accumulation points will have to be on the boundary if gamma is discrete anyway, right? And this doesn't depend on the base point. Right, so it's just...
So just to be sure, the phi t sub HD is just apply the flow to x and then apply the differential to v. Okay.
No, so maybe I should say of T1 HD. It's the geodesic flow on the unit tangent bundle of HD. Right? So you need V to define it already to know how x is moving. Right? It's just moving on time t along this geodesic, right?
The second characterization holds for any discrete gamma.
Very true. Yeah. Yeah. Yeah, so I'm not going to do the whole proof, but this is one of the exercises actually to, if you've never done this, you want to learn about hyperbolic dynamics and subgroups of isometries of the hyperbolic space, you'll definitely have to do these computations at least 10 times in your life. Yes?
A question related to Fanny's question. So, Fanny, you said, are these equalities true for any discrete subgroup?
The second one here, non-rendering set is this. Yeah. But the first one doesn't make sense in if you don't have this convex set C, right? So, yeah. And also for the whole.
You could have a convex set that's preserved, but the action is not co-compact.
Yeah, but then I don't know. Because really the implication that I want to think of is that if gamma is convex co-compact, then the flow is axiom A. I don't care much about the other one.
And you said that the second condition is automatic? Like axiom A has two conditions?
Yeah, well, three actually. There's 1, 2, 3 here. I'm saying that the condition, the third condition will be automatic.
If the first
No, axiom A.
Anosov's closing lemma.
These two conditions.
Sorry, where? Oh, the condition on this. Oh, yeah. This will be automatic also. This is. In that setting, it's easier, right? It's just it's the fact that fixed points of hyperbolic elements are dense in the limit set, right? However, the fact that an Anosov flow is axiom A is the Anosov closing lemma.
The set C needs to be 18 invariant or 5T invariant or something, or C could be chosen to be a single point. It's a convex set. Like, what's the condition on C in the definition of axiom A?
So here, so this is a definition of convex co-compact, right? And the condition is that it should be convex, really. Like when you have 2 points in there, the geodesic stays in there. Yeah. All right, are there other questions or? Okay. So now let's move to the other part of the title, which is Anosov representations. Okay. So Anosov representations are things that take a while to get used to in some way, right? If you were to just give a definition like this, it's not obvious to understand why the definition is interesting, why it's important. I guess this happens with many things. And also, if you want to go deep into Anosov representations, there are quite a few different theories to understand to start with, right? So an Anosov representation will be a representation rho of some discrete group gamma into some Lie group G. And this discrete group will have to be a hyperbolic group. For definitions will come later, by the way. So this will be a hyperbolic group. And this G here will be a semi-simple Lie group, real Lie group. And add your favorite adjectives. Yeah, you know, like, well, essentially, like finitely many connected components and finite center should be the appropriate ones here. And non-compact, unless you want. Sorry?
Linear.
Not even linear, actually. It's not clear. No, it's not quite linear with this, but anyway. I think the right definition would be you want to have Jordan projections. to be well defined. That's the, anyway. But anyway, for at least the first 3 lectures, our G is just going to be SLN. Right? So well, I like to write it at SL of V with some vector space V. Right? So V will be like some real vector space, finite dimensional. This dimension will be called V. And for hyperbolic groups, I won't get into the general definitions of hyperbolic groups. That would just be too much. But actually, we now have examples which are convex co-compact subgroups in hyperbolic geometry. Right, so these in yellow, these are examples. And actually, you may even restrict this to the case where gamma is a co-compact subgroup. So like convex C could be the whole hyperbolic space HD, and then the limit set lambda gamma will be the whole boundary of the hyperbolic space. And you can even assume that this is the 2-dimensional hyperbolic space, and that gamma is just a fundamental group of a closed surface of a genus at least 2. This is what the theory was built for in the first place anyway, right? So, and when you go into definitions of Anosov representations, you have to make some choice other than just the Lie group G, which is of some, well, you have several ways of stating this. I like to state it in terms of flag manifolds. So say a pair of opposite flag manifolds. You could see this as a choice of some subset of simple restricted roots. And for our examples, this will just F plus will be the projective space, and F minus will be the projective space of the dual space V star. Okay. And the one thing that you'll always see with Anosov representations when you want to understand anything about them are limit maps. Right, so the limit maps, they're essentially replacing these limit sets that you have with subgroups of isometries of HD. Right? And the appropriate conditions, so these limit maps, there will be, let's say, some map xi from the boundary, the Gromov boundary of your group gamma to the flag manifold F plus, and you'll have another one, let's call it xi star, into the other flag manifold. Right, in our example, this boundary of gamma will just be the limit set, right? So you can just think of this as xi from lambda gamma to the projective space, xi star. Yeah, you never put too many squiggly things on xi's. Xi star will go to the projective space of the dual space. And they come with a transversality condition. Which is part of the stuff that we'll have to explain. And this transversality condition is that if you put the map, well, you put the two maps xi and xi star together as one map from pairs of elements in the boundary to the product of your flag manifolds, you want this to send different distinct points to what we call transverse flags. Right? So you want this to send this space here, this when I put a parenthesis around the 2, it means that it's distinct pairs. And you want this to go to transverse pairs. Right, and in our example here, I realize that my color code is already messed up. I don't know if this is visible here, if I go that far here. When your flag manifolds are just the projective space and the projective space of the dual, transversality means that, well, there are two ways of interpreting this. If you see the projective space as an element in there as being a class of a vector v, right, up to multiplication by some number. The other one would be a class of some linear form alpha up to multiplication by some other number. And the condition is that the linear form alpha evaluated on v should not be 0. Right. The other interpretation being that you can see these as Grassmannian manifolds instead, P of v being the space of lines, and P of v star being the space of hyperplane, and you want your line to not be inside the hyperplane, but to be transverse. Okay. All right, I guess it's time for some switching. Now what we're going to want to do is to use these things and to study them with something that replaces the geodesic flow for hyperbolic geometry. If you're to do higher rank groups from a geometric point of view, the usual thing would be studying symmetric spaces associated to this. Now the thing is, if you study the geodesic flow of the symmetric space in higher rank, it will not have these hyperbolic properties. There will be some central direction, so there will be some partially hyperbolic stuff. And so what we are trying to do here is to get some actual, well, what we want in the end will be some axiom A flow. Right? And if you go back to the unit tangent bundle to the hyperbolic space and look at the geodesic flow here. So far we don't have a replacement for this, but we have a replacement for what should be the orbit space of this. Right, just knowing the orbit of the geodesic under the geodesic flow of a pair x and v is the same as knowing the endpoints v plus and v minus. Right, this is the map sending x and v to v plus, v minus. And fibers of this map are exactly orbits of the geodesic flow. But now, what is going to be the replacement for this space here of distinct pairs on the boundary is going to be the space of transverse flags here, or transverse pairs in projective spaces. So the idea will be to construct some space that we'll call L because it has to be some sort of line bundle, right? It's one extra dimension compared to the orbit space. So we want to find such a space L that fibers over this space of transverse pairs with a flow acting on L such that the fibers of this map are exactly the orbits of this flow phi t. Okay, and now that this question has been asked, the answer is pretty simple. Pairs in here, they are consisting of a vector v and the linear form alpha up to multiplying both by numbers, but by two different numbers. If you want to add one dimension, you should restrict one of these degrees of freedom there. And so what you'll do is consider v and alpha up to multiplying them by the same number. So this means that we're working in the space which is the projective space of the direct sum of v and v star. Right? It's v and alpha up to multiplying them by the same number. Now this is not a homogeneous space under the action of SL of v, but it has three orbits. Right? And the invariant under the action, which by the way, the action is that if you're acting on such a pair, you're just multiplying, acting on v, but on alpha, you have to compose with the inverse of v for this to be an action, left action here. All right, so v and alpha are defined up to multiplying them both by the same number. So applying alpha to v is still not well defined. But if you multiply v and alpha by a number lambda, and you look at what happens to alpha v, it will be multiplied by lambda squared. Right? So the sign of this thing is well defined. And so we're just going to look at where this is positive. So there are three orbits for the action of SL of v on this projective space here, this being positive, 0, or negative. Right? And if you look at this space here, there is a, so this is a definition, by the way, of L. There is a natural map going from there to transverse pairs, which is sending this v alpha to the pair, the class of v and class of alpha. And what we need to add now is this flow. Right? Is to find a flow on L such that the orbit space will exactly be this space of distinct pairs. Right? So here we're considering vectors and vector and the linear form up to multiplying them by the same number. So for the flow to be non-trivial, we're going to multiply them by different numbers. Right? So for this to be a flow, let's multiply v by exponential t and alpha by exponential minus t. If you're trying to find a flow that has some contraction and dilation properties, this is probably the first one you'll think of. Right? And if it doesn't give you a hyperbolic flow in the end, you're doing something wrong. Right? All right. And it's now time to state a theorem. Which a good chunk of this course will be based on. So this is something we did with Benjamin Delarue, so myself and Andy Sanders. So you start with an Anosov representation. So gamma is a representation, rho is a representation of gamma in SL of v. And so this is what I still like to call projective Anosov. People call it P1 Anosov or even just 1 Anosov these days. It doesn't matter because I haven't defined it yet. And what you want to say is that the quotient flow of this thing here by gamma will be axiom A. You cannot do this quite though. Because if you want to consider a quotient of L by your group gamma, this in general will be a very bad space. this has no reason to be a manifold, because the group gamma will not be acting properly discontinuously on there, right? So this is out of question. And the reason for this is that if you think that the only way of describing a homogeneous space is to see as a coset space, G mod H, you might want to see L as, let's say, SLDR mod some subgroup, and this subgroup will be essentially SLD minus 1. Essentially, because there's a plus minus here, it could be determinant minus 1. And then your flow acting will just be a diagonal flow acting on this quotient space. Right? But this isotropic group here is non-compact. Right? This non-compactness means that SLD acts non-properly in here, so usually you don't have nice quotients. So the first part of the theorem will be saying that actually you do have a nice quotient, not for the whole L, but just for an open set in L. So there exists, we'll call it M rho hat, an open set, which is invariant under rho, and also invariant under the flow phi t. Such that the action of gamma here is properly discontinuous. And the quotient flow of M rho hat is axiom A. So we'll call it phi t rho on the manifold M rho. Is axiom A, right? Where M rho, by definition, is the quotient of this M rho hat.
So is it an implication or equivalence?
That's an implication. All right, so the two important results here is this properly discontinuous action and the axiom A of the quotient flow. Yeah?
Is there a way to see, and is phi t coming somewhere from homogeneous structures? Is it some subgroup of SLDR acting somewhere, or is it just something else we've defined?
The flow phi t?
Yeah.
Yeah. It's a diagonal flow.
Okay.
Yeah.
Flow. Okay.
It's just multiplying, you're taking quotients from the right action, and here it's like phi t L. If you call this group H, this one G, phi t L of some GH will be multiplying G on the right by exponential Tx, and your X will be a diagonal matrix, right? X will be essentially 1, and then some minus things to make it have trace 0, right? So minus 1 over d minus 1, minus 1 over d minus 1.
Center of the levy.
It is the center of the levy of this case, yeah.
Stands for levy.
Actually, not that L, no. Yeah. It stands for line bundle, because this isn't a fine line bundle. This thing here has trivial dynamics, and meaning that this is an R principal bundle, essentially. All right. All right, so what we're going to, are there any questions actually at this point? Yeah.
The projective Anosov, the difference between the Anosov and the projective is that we pick the G to be SLV.
Yes, exactly. We pick the G to be SLV and the flag manifolds to be the projective space and dual projective space. Yeah. Yeah. Yeah.
Unique is the same at
It's a good question. You might want to, if this M row hat is unique. Well, if you want some uniqueness, you have to make it as big as possible, essentially, right? And I do believe that the construction we have is probably the biggest one that works, but I haven't checked it, right? And I think it's the type of question you could probably answer by having a close look of some work of Leon Cardarales and Florian Stecker on discontinuity domains. But I'm not quite sure. There's also a joke here, which is the case where gamma is elementary, where essentially you should have, sometimes in the axiom A, the definition of axiom A, you'll see that you assume also that the non-wandering set does not consist of a single periodic orbit or of finitely many periodic orbits, if it's just looking at a basic set. And because here, if gamma were to be Z, you have a notion of Anosov, and then then M row hat will be definitely not unique because there's like a choice of an orbit in one direction and corresponding to an element gamma in the group, and another one corresponding to gamma inverse somewhere else. But yeah, that's probably not worth spending too much time on. Yeah.
What do you get when V is 2 or 3-dimensional?
Yeah, so when V has dimension 2, the group is SL2, so this is the isometries of H2, right? And it's actually one of the exercises in that this is the same as the unit as the geodesic flow of the unit tension bundle of H2. Yeah.
And in dimension 3?
In dimension 3, it's also an exercise to do some pictures. The thing is, to explain dimension 3 some more, you'd have to explain more about Anosov representations in dimension 3, which might happen at some point. Will definitely happen in the exercises, but maybe even in the lectures, we'll see. Let me see. Yeah, I'll have to bring this one there.
The quotient space M row is compact?
No. Oh, that's a very good remark, actually. Yeah, no. M row is not compact.
Okay.
But in the definition, that's why in the definition of axiom A flow, I think I messed myself up here. Right. We're good. So in the definition of an axiom A flow, M does not have to be compact, but the non-wandering set has to be. Right. So part of the proof of this theorem we'll be checking that the not only that you have this M row hat on where gamma is acting properly discontinuously, but you also have to find a subset of this on which gamma will be acting co-compactly. And that subset will correspond to the non-rendering set in the quotient. Right? So there will be some co-compactness to prove, but not on M row hat. This will not be compact. Right? Because actually, if you think just of the dimension 2 case, where this is just the geodesic flow of H2, and if you have a convex co-compact subgroup, this will be actually, M row hat will be the whole unit tangent bundle of H2 in that case. So the quotient will not be compact. Okay. So right. So there's also a version of this for arbitrary G and arbitrary flag manifolds that I'm hoping to get to by probably the 4th lecture or something. And also something else, which is that this flow is more than just being axiom A. It has a lot of nice dynamics. So the statement that we prove in that paper is that it has it's exponentially mixing, which not all axiom A flows are.
Sorry, so the non-boundary set is unique like the convex co-compact thing?
Yeah, the non-random set has a dynamical definition anyway, right? So it's once you've defined this flow, it's uniquely defined.
So it does not depend on m row.
Oh, I see what you mean. Yeah, no, definitely. Yeah, there's this non-wandering set. If you were to have different m row, they will have to contain the same non-wandering set, at least for the non-elementary case. For gamma, is not just that. Yeah, or virtually said. All right, so essentially the plan of this mini course will be to try to prove this theorem, but it's mostly an excuse to introduce Anosov representations and try to say a bunch of things, and including talk about their definitions. So the first part will be about proper discontinuity. So essentially, we're trying to construct this M row hat here, right? And prove that the action of gamma on there is properly discontinuous. And there are a few key notions that we need to be familiar with before we can do anything like that. The first one is proximality. Before we can talk about proximality, I'll use the same notation throughout for the eigenvalues, which is that if you have G in GL of V, I'll use lambda 1 of G, lambda 2 of G in this order to be, well, the Jordan projection if you wish, or the, actually not the Jordan projection in GLV, but in SLV. And so these are the logs of the moduli of the eigenvalues. Okay. Okay, so proximality is something that has several characterizations, so we're going to start with a good old proposition / definition. So you take an element G in your linear group GL of V, and we'll have three characterizations here. So the following things are equivalent. The first one would be an algebraic description saying that lambda 1 is different from lambda 2. So essentially the highest eigenvalue is an eigenvalue for only one direction, and it will have to be real. And the second definition will be one more of differential geometry, which is that you look at the action of G on the projective space, right? And you ask for this action to have an attracting fixed point. Right, so attracting meaning that the differential at this fixed point is contracting. Yeah, so you could say lambda 1 of this thing is negative. And the third condition would be something of topological dynamics. It's saying that you can find a line, let's call it L plus, a hyperplane H minus that we'll assume to be transverse. Such that pairs of G will send everyone to L plus, except possibly if you're in the projective basin of H minus. So here I'm using this identification between hyperplanes and the projective space of V star, by the way. Right, so for any L which is in P of V, if L is transverse to H1, to H minus, then as k goes to plus infinity, gk acting on L will go to L plus. Right, so having these source sinks dynamics, like an attractor and a repeller. Right. And the whole dynamics, whenever you take something which is not in the productization of H minus, it will go to L plus. I'm not going to do the proof of this, which is just linear algebra. But we do need to understand what these L plus and H minuses are in terms of the matrix. Oh, I should also give the definition. But G is called proximal if these are satisfied. And so if G is proximal, then these L plus and H minus, so the attracting fixed point L will be the same as the L plus in this other definition, and we'll use the notation L plus of G. These are uniquely defined. And what are they? Well, essentially, L plus of G, this is a fixed point in the projective space. It's just an eigendirection, right, for G. So this is the eigendirection for sorry, it's the eigendirection of G for the eigenvalue, well, corresponding to lambda 1, and this H minus will be the same the eigendirection of the transpose of G for its largest eigenvalue, which is the same as the largest eigenvalue of G. Right. So transpose being just mapping alpha to alpha composed with G. Well, then it's also the eigendirection of G transpose inverse for minus lambda 1. Yeah, no, it's for the same. Yeah. Yeah, no, it's not lambda D. It's not minus lambda D. It's definitely, lambda 1. Because we're working with transverse things and not with the usual thing in flag manifolds, so that's why it's. Okay, I should probably ask when we started, just to have an idea of how long I have.
You probably can go for 5 more minutes.
5 minutes, okay.
Made a lot of announcements at the
Yeah. Okay, thanks. I should, because I want to get us to some definition of Anosov before the end. Right, I might want to say one word about hyperbolic groups. Before we go further. Right, so as I said, the example that you only need to keep in mind for hyperbolic groups will be a convex co-compact subgroup acting on HD. And the important notion that we'll use is the boundary. But you have to remember that this boundary, well, is a boundary. It's at the infinity of gamma. It comes from a compactification of gamma, right? So a hyperbolic group, without giving the definition, comes with a compactification, and this is a theorem. where it's gamma and adding this boundary that we call the Gromov boundary. And which, in the case of a convex co-compact subgroup, this is just considering gamma as the orbit of some point, right, inside the hyperbolic space. If gamma has torsion, pick a point that is not fixed by anyone, and add to this orbit its accumulation points at infinity, right? Right, the important thing is that you actually have notions of sequences in the group gamma converging to this boundary. That's why I want to state this. And in the case of a convex co-compact subgroup here, it just means that the orbit goes to this point of lambda gamma. And the properties of this action that we'll use over and over. The first one would be that if you have an infinite order element in your group, then it has exactly 2 fixed points in this boundary. So I'll use gamma infinity to mean infinite order elements. And these fixed points that I'll call gamma plus and gamma minus are simply the limits of the powers of gamma k. Right? So these exist and are distinct. Yeah, I should probably move to this, it'll be easier. All right, we're going to be moving to the right after this, sorry. And the second condition, which is very close to being a defining condition of this action, is what we call the convergence property. Okay. Which is that if you have a sequence gamma k in your group, and if gamma k converges to some point in the boundary, call it gamma plus, and the inverses of gamma k also converge to some point, gamma minus, then when you let gamma k act on any point except possibly gamma minus, it will converge to gamma plus. And this is uniformly on compact subsets. All right, it's soon going to be time, so maybe what I'll say to conclude this is that, so this convergence property, right, this has this simple picture that if you have your sequence having these limits gamma plus and gamma minus, everyone is going to be sent by the sequence gamma k, whether it's in gamma or on the boundary, going to be sent to gamma plus. And the idea of Anosov representations is going to essentially mimic this action here on the projective space and the dual projective space. But not only that, but in a way that is compatible with the original action of the hyperbolic group gamma on its boundary, essentially. Right. So this is something that we'll see on Tuesday. I'm going to stop here.
Questions for Daniel?
Maybe you mentioned this, but is there an explicit and easy description of non-wandering sets in terms of the limit sets of
Yeah. Yeah, definitely. So this is going to be part of the essentially this, oh actually maybe don't even need to add it. It's almost already here, right? So you'll have limit maps for an Anosov representation, going from distinct pairs in the boundary to transverse pairs, right? It will just be the preimage of this in L. That will be the non-wandering set. Right. So for example, periodic orbits. A periodic orbit, it just means that, maybe let's write it here. If you have in the quotient m rho, say you have some phi t rho of x which is equal to x. When you lift this to m rho hat, it lifts to some v alpha in m rho hat, such that phi t rho of v alpha is not equal to v alpha, but is in the orbit of v alpha. Right? Is some rho of gamma applied to v alpha. Right? So rho of gamma applied to v alpha is phi t. Sorry, say here is we're in the lift on the L. So this is exponential t v, exponential minus t alpha. So it's saying that v should be an eigenvector of rho of gamma for this eigenvalue t, and alpha should be an eigenform. And so m rho hat will be defined in a way to remove all possible eigenvectors except from the one corresponding to lambda 1, to the highest eigenvalue. And this will be the image of psi of gamma plus under this limit map, essentially. I'll explain all of this next time, by the way.
One more quick question.
Just what do you mean by gamma k goes from x to gamma plus?
So that's the whole thing that, so x could be either in the group gamma or in the boundary. Right, it's in the compactification of gamma. So the whole thing is that there's a topology on gamma on this compactification, right? That it definitely did not do.
I think it says gamma k at x.
Oh, sorry. The dot should be higher, right? Is that the thing? It should be a backslash c dot instead of backslash dot. Yeah, it's gamma k acting on x. Right, oh, actually, that's an important thing that I didn't state, yes, is that the action of gamma on this compactification, so gamma acts on there, and this is extending the left multiplication on gamma. Right.
All right, let's thank Daniel again.